Hey guys, and welcome back to another video on the channel. In today's video we're going to be trying this integral. So the integral from 0 to pi on 2 of x over tan x with respect to x. So what we're going to do with this one pretty much is we're going to change how it looks and then pretty much parameterize it. So what we can do is at the moment we want to try and figure out how we can cancel out this tan x without pretty much integrating it yet. Because at the moment that's pretty much the biggest problem with this integral. But if we parameterize it in a correct way, when we differentiate under the integral sign, we can actually cancel this out. So what we're going to do before we even parameterize anything, we're just going to change how x looks. So x is actually the same as just tan inverse of tan x, is it not? Because if you apply tan inverse to tan x, it'll just become x. So this is a valid substitution you can make right at the start before you pretty much add in any parameter of any kind, pretty much. So it'll be the integral from 0 to pi on 2 of tan inverse of tan x all on tan x. Now the reason why I chose this one is because when I differentiate this with the parameter, the tan x will cancel out with the 1 over tan x, because that can be treated as a constant pretty soon. So what we're going to do is pretty much, alright, we're going to insert a parameter pretty much in here and then differentiate with respect to it. So this is pretty much Feynman's technique of integration. So we're going to let f of alpha be this integral, and we're going to put alpha right next to the tan on the inside of the tan inverse. So tan inverse of alpha tan x all over tan x with respect to x. So this would be f of 1. So this is when alpha is equal to 1. So what we're going to do is pretty much break down this integral now, and then for our final answer we'll substitute in alpha equals 1, and that will give us our integral pretty much. So what we're going to do is differentiate with respect to both sides. So differentiate with respect to alpha of our integral from 0 to pi on 2 of tan inverse of, forgot the alpha, alpha tan x all on tan x dx. So what we can do now is, because we've got this here, we can pretty much move this operator onto the inside and change it into a partial derivative. And the reason why that's good is because if it's a partial derivative, any other letter that isn't alpha is treated as a constant pretty much. So that pretty much means we're just going to be differentiating just tan inverse of alpha pretty much, and the tan x will be a constant. So what we can do is we can move that operator on the inside and just change the symbols really quickly. So it'll be f dash of alpha is equal to the integral from 0 to pi on 2 of the partial derivative with respect to alpha of pretty much all this. Now, what we can actually do is we can actually move this guy outside of the derivative into the integral still, because it doesn't have any alphas in it. So it's pretty much independent of this operator. So what we can do is just move that out. So we'll have f dash of alpha gives you the integral from 0 to pi on 2 of 1 over tan x, which is the one we've just moved out, and then the derivative with respect to alpha of tan inverse of alpha tan x. Now, when we differentiate this, what we're going to get is pretty much, alright, the differential of the inside, which will be tan x. So what we're going to have is integral from 0 to pi on 2 of 1 over tan x. If you're differentiating this, we're going to, oh, that's not a highlighter, move that. When we're differentiating this, differentiate the inside function, which is going to be tan x, so we'll have times by tan x, and then it will be 1 over pretty much all of this squared. So alpha tan x all squared. Okay? So hopefully you can see how I got that, because if you were to differentiate just, let's say, x over a with respect to x, you would get a on x squared plus x squared. So hopefully you can see where I got that from this bit here. Pretty elementary differentiation, but it's a bit funny with the parameter involved. Now you can see, hopefully, that we can cancel these guys out. So all we're left with pretty much is the integral from 0 to pi on 2 of 1 over 1 plus alpha tan x squared. Okay? So remember, this is f dash of alpha. So now what we want to do is we want to keep breaking this down, because at the moment we can't really integrate anything at the moment. So what we're going to do is try and break this into partial fractions. But before we do that, we're going to multiply pretty much the top and bottom by sec squared with respect to x. So technically we're timesing it by 1. So we multiply it by, alright, sec squared of x over sec squared of x. Now the reason why I want to do that is because I want to take advantage of one of Pythagorean's identities, that sec squared of an angle is equivalent to 1 plus tan squared of an angle. So if I do that, I can pretty much change the bottom very quickly. So if I do that, I'm not going to distribute pretty much the sec squared to both of them. I'm just pretty much going to insert this identity. So all I'm going to do is replace this bottom bit with pretty much this. So what I'm going to get is f dash of alpha is equal to the integral from 0 to pi on 2 of sec squared x all over 1 plus tan squared x times by 1 plus brackets alpha tan x all squared. Okay. So you're probably thinking, oh, we've got something a bit more worse off. Well, not really, because once we make a substitution, this is all going to pretty much go away. Now the reason why I wanted the sec squared on the top is because if I make a substitution saying let u equal tan x, if you were to differentiate that to get its differential, so we get du equals, and if you differentiate tan, it gives you sec squared x dx. So in other words, dx is du on sec squared x. So what we're going to do is pretty much, alright, we'll cancel that out anyway, and now we're going to get something really easy on the bottom relatively. So if we pretty much apply that, we've got to also change our bounds. So when x equals 0, u will also equal 0, because tan of 0 is still 0. Now this is the tricky bit here. When x is pi on 2, that's technically undefined. If you were to go tan inverse of pi on 2, you would get undefined. But if we take a look at the curve, the tan curve, this is pi on 2. As tan approaches pi on 2, it goes off to infinity. So what we're going to say is, alright, this is basically infinity. So in other words, we're going to rewrite this integral. So I'm going to just copy this real quick and write it down below. Copy. Paste. So this integral pretty much turns into this. So f dash of alpha turns into, alright, integral 0 to infinity of, I'll leave this for a sec because I'll show you where that cancels out, over 1 plus u squared on 1 plus alpha u all squared du on sec squared x. So that cancels out, and all we're left with is pretty much the integral from 0 to infinity du on 1 plus u squared on 1 plus alpha u all squared. Right, now we've got this. So we've done a lot of manipulation, and this is definitely a very hard integral, definitely not beginner's level, but we're breaking it down, aren't we? So f dash of x, alpha, 0 to infinity on, let's just go 1 over 1 plus u squared on 1 plus alpha u all squared du. Now what we're going to do is pretty much apply the cover-up method. So pretty much we want to work out, alright, when does this bottom bit equal 0? So in other words, we have 1 plus alpha squared u squared equals 0. And we're going to solve for u squared because we have a u squared here. So we discover u squared is negative 1 on alpha squared. So in other words, we will rewrite one of these bits here as pretty much, alright, this top bit. At the moment, we could rewrite it as 1 plus negative 1 on alpha squared. But we can see we can multiply the top and bottom by let's go positive alpha squared in this case here. So we would get alpha squared on alpha squared minus 1. So we can rewrite the top bit as alpha squared on alpha squared minus 1 all over 1 plus alpha squared u squared plus, and now we're going to do the other side. So when this equals 0, so you have 1 plus u squared equals 0, so therefore u squared equals minus 1. So we can rewrite that as 1 over 1 minus alpha squared. So that would be 1 over 1 minus alpha squared all over 1 plus u squared du. So if you want to go take a look at what I've just done there, I've done the cover up method because we don't really have any numbers with this partial fraction, so you have to use the cover up method. So if you want a better or fuller explanation of that, the reason why I'm doing this is because I've just got to finish this video because I've got to get out pretty much till breakfast. But if you want to search at the cover up method, take a look at that. That's pretty much what I've done there. Right, so let's write this out really quickly. So it will be f dash of alpha is equal to, alright, the integral from 0 to infinity of alpha squared on alpha squared minus 1 all over 1 plus alpha squared u squared plus 1 over 1 minus alpha squared all over 1 plus alpha squared du. Now it looks pretty complicated at the moment, but we're going to change how this looks. So at the moment I want to factor out pretty much a 1 over alpha squared plus 1 or a 1 over alpha squared minus 1. And we can see we've almost got that at the top there. And the reason why I can do that is because it's independent of u. It's a parameter. So what I can do is actually change how this middle bit looks by changing that to a negative and that to a negative. So if I do that, then that turns into pretty much this. And I can factor out, alright, 1 over alpha squared. Oh, let's write that a bit better. 1 over alpha squared plus, minus 1, sorry. Minus 1, and then the integral from 0 to infinity of alpha squared on 1 plus alpha squared u squared minus, and this will be 1 over 1 plus, I've written something down wrong. That's not an alpha, that's a u. My mistake, so I didn't carry my u here. That would have been a big error. U, and then that's a u squared. Okay, du. Alright, cool. Now, after all that manipulation, we can finally integrate it. So we can see we've got a tan inverse here. So what we're going to have is, alright, and this is still equal to f dash of alpha. So f dash of alpha is 1 over alpha squared minus 1, and now we're going to integrate it. So this first one here, when you integrate it, we can see we've got alpha squared, so we're going to have, alright, pretty much an alpha squared. Then we're going to have 1 over the differential of this inside bit, so alpha squared u squared is the same as alpha u all squared. Differential of that is 1 over alpha, so 1 over alpha, and then we're going to have tan inverse of just alpha u in this case here. So that's that bit integrated. Now this bit here is just going to be minus tan inverse of u in that case here, because the differential will be 1 and it doesn't really change at all. And our bounds are 0 and infinity. Okay, we're almost there. We can simplify that. That's going to be alpha and that's going to be gone. So what we're going to have is pretty much, instead of there, we'll just have an alpha tan inverse of all that. So I'll bring that closer together real quick. There we go. Alright, so now we're going to substitute our bounds in. So f dash of alpha is 1 on alpha squared minus 1, square brackets still, because this is going to get multiplied by everything. Substituting in infinity first, we're going to have alpha tan inverse. Now, if we plug in infinity at the moment, we're going to have pretty much alpha times infinity. But we haven't defined which infinity it is, because we can't say it's pi on 2 straight away, because it depends which one we've said. If it's negative, then it'll be pretty much this one over here. And if it's positive, it'll be this one. So at the start, we have to change our parameter real quick and say, alright, alpha is greater than 0, and then we're all good there pretty much, okay? So that'll be a positive number there. So that'll be going out to positive infinity, minus tan inverse of infinity, it'll be positive, minus brackets around this, alpha tan inverse of 0 will be 0, minus tan inverse of 0 will also be 0, brackets. So that's all gone, that's 0, and now we're pretty much going to evaluate these little bits here. So this turns into pretty much pi on 2, and this also turns into minus pi on 2. But this is times by alpha, so what we have is pretty much, alright, f dash of alpha is 1 over alpha squared minus 1 of alpha pi on 2 minus pi on 2. What we can do is take out a factor of pi on 2, so I have pi on 2 out of pretty much 1 on alpha squared minus 1 multiplied by alpha minus 1. And we can simplify this a little bit because we can change the bottom bit of this fraction here, because alpha squared minus 1 is the same as alpha plus 1 multiplied by alpha minus 1. So we can see we've got something in common there, so I have pi on 2, there's equal sign there, multiplied by 1 on alpha plus 1 multiplied by alpha minus 1 times by alpha minus 1, and we can see that cancels out really quickly. So all we get is f dash of alpha is pi on 2 multiplied by 1 on alpha plus 1. Righto. Now we're going to integrate with respect to alpha on both sides. I can leave the pi on 2 at the outside because it's independent, because it's a constant, so I get f of alpha is equal to pi on 2 natural log of alpha plus 1 plus c. Now, we have to work out what this plus c is. So let's remember what we originally defined f of alpha to be. So our original integral was this, the integral from 0 to pi on 2. I believe it was, it's all the way up here. There it is. Let's copy that. Copy. And bring it down here. Paste. That's our original integral. And this is equivalent to, let me get the pen, pi on 2 natural log of x plus 1 plus c. So if I let alpha equal 0, that's going to be 0 because that'll be natural log of 1, and that will be 0 there. So our c will be 0. So in other words, the integral from 0 to pi on 2 of tan inverse of alpha tan x all on tan x dx is equal to pi on 2 natural log of alpha plus 1. Now, our original integral was when alpha equals 1, and our original integral was pretty much just x on tan x, so integral from 0 to pi on 2 of x on tan x, substituting in alpha equals 1. Our answer is pi on 2 natural log of 2. Ta-da! There we go. Nice quick little video for you. Very complex. But yeah, I hope you enjoyed this video. I've got to go meet up with my mate. We're having lunch, and then yeah, gonna go to uni. Alright, I'll see you in the next video.